On the transceiver architectures. So last time we discussed the heterodyne receiver mainly, and we even did not finish all the types of heterodyne receiver. We discussed the classical representation of the heterodyne receiver, the receiver that takes the signal or the received signal to an intermediate frequency. Tamam? Doesn't really bring it down to zero frequency. And then, of course, at stages later, it has to be brought down to zero frequency. But the idea here is, in most of the cases, you bring it to an intermediate frequency, and then you perform something called envelope detector, اللي هو simply diode resistor or capacitor. Then that is going to trace the amplitude of the sine wave, and accordingly, it brings the signal down to zero frequency. But in terms of oscillators or multiplication by other frequencies and so on, you don't bring the signal all the way to zero frequency. This is the whole idea of the heterodyne receiver. Now, in addition to that, there are other more modern approaches to heterodyne receiver, and we are going to discuss a couple of them today, or a couple of features of modern heterodyne receivers, and then we will move to other architectures of transceivers. Before doing that, just one practical aspect here, a reminder from what we did in chapter 2, the part that talks about the nonlinearities and the issues with RF communication electronics in general. In that part, we have discussed a circuit that we ended up saying that this circuit can be used as a mixer. You remember that circuit? Yes. The one that has two inputs, and then the finding that we found eventually that the output of this is going to be somehow the multiplication of those two signals together. One of the signals is controlling switching on and off, and the other one is put as an input to the system. The output that you will get from here is going to be something like multiplying those two signals together. Tamam? That's basically what a mixer is doing, multiplying two signals together in an analog form. Okay? So you also remember that because of the fact that this signal is controlling a switch rather than being really directly multiplied, it becomes as if you are multiplying a squared version of this signal with V2, Vn2. Tamam? Remember from your signals and systems, if you have something like this, a periodic square function, okay, the frequency components of this periodic square function, they span infinite number of frequencies, right? It becomes a Fourier series summation of the fundamental frequency, which is the basic frequency here, and then another component at double that fundamental frequency, and then another component at triple that, 4 times, 5 times, and so on. These are called the harmonic extensions until infinity. You add until infinity. Tamam? The result of this that we discussed already before is that the outcome that comes from oscillators in general suffers from something called Spurs of the mixer. Okay? That you don't end up only with your intended frequency that results from the multiplication, but you end up with harmonics, more factors into your system. Okay? So that's something just to keep it in mind. We are not going to use it now, but it's going to come later in the discussion, not today. Okay? This, in general, two things. Mixers are producing harmonics. We call them mixing spurs, that they happen due to the design of mixers. And the other thing is, based on this, we know that mixers are kind of, you can think of it as kind of noisy component. It's not noise here, but it's distortion. So they are components that introduces a lot of distortion, and they are one of the hardest parts of your RF transceiver to design. So the design of mixers is one of the most difficult ones, specifically to get good characteristics out of them. And we'll see that later when we talk about the design of mixers themselves. Okay, so we'll come later in the course to discuss the design of mixers. We will go back to this Spurs issue and also other difficulties in mixers design. Yeah. Omega n هنا. Okay. So omega n is the input frequency. تمام. Omega n احتمال n دي تكون غلط.
I think it should be n, yes.
Huh?
It's the IF mixer.
Yeah.
IF mixer produces omega n plus m omega 0, and I think t is type.
I think this is a typo. It's omega n plus or minus. So this is a typo. Yeah. Now.
What's omega n and omega I and t?
Okay. So modern heterodyne receivers, two characteristics of the modern. That modern here, by the way, the book is old. So when we talk about modern here, it's something like maybe 15 years old or more, or 20 years old. Okay, so it's not really modern like of today's. Okay, but the more trendy ones, they use two characteristics. Number one, they have a 0-second intermediate frequency. Remember, if we go back to the, I don't have the slides for that here now, but if you go back to the previous lecture, you will find that towards the end we talked about two stages heterodyne receivers, and in those two stages heterodyne receivers, we bring the signal to an intermediate frequency 1, and then we bring it again to intermediate frequency 2, which is smaller than intermediate frequency 1. And we described why we can do it in two stages. It simplifies the design. It makes specifically the design of intermediate filters so that they can do the job of image rejection and channel selection in an easier way. Okay? But that comes with a challenge, the fact that now you suffer from the image 2 times. So it's not only one stage where you suffer from the image, you suffer from the image in 2 stages. First IF and then second IF. Tamam? With the advancement now, when we talk about just one thing, because I didn't mention that from start. So when we talk about the advancement of RF transceivers, the advancement here is talking about the advancement in chip technology. Because the whole idea here is we are talking about RF integrated circuit design. So we are talking about when you are trying to design your transceiver to fit on a chip, a single chip, right? And with the advancement of the technology, things that have not been doable within the chip, and you had to take those components outside the chip because of size, because they need larger size, so they cannot fit inside the chip, or they need some passive components that cannot be implemented within the constraints of the chip, or they suffer from high undesired effects such as high nonlinearities or high interference effect on other modules and so on, as we will see when we talk about the other architecture of the transceiver. Then you have to take them outside chip so that they do not affect the other components, right? So there are many reasons for this. With the advancement of chip design and manufacturing technologies, more of the things that have not been possible to do in the past becomes possible. So the idea here is not that the technique itself is not workable, it's that the technique cannot be integrated into a circuit without bad effects. And then when the technology advances, the techniques become more suitable to be integrated inside the chip without most of the bad effects. Okay? So with the advancement of RF integrated circuit technology, this option, the 0-second IF, became a viable option that can be implemented on a chip. So basically, in this case, first stage brings to an intermediate frequency, second stage brings you directly to 0, without the use of envelope detectors and stuff like that I mentioned at the start of the lecture, right? So now you are going to 0 frequency or the baseband signal directly by 2 mixers or multiplications or demodulators, one after the other. So one in intermediate frequency, and then the second one takes you directly to the 0 frequency. The nice thing about this is when you go directly to 0 frequency, you end up getting rid from the second image problem, right? Whenever you are not doing intermediate frequency, you don't have an image problem. However, there is something called self-image problem, which is that the signal itself becomes the image of itself when you are trying to demodulate. Okay? When you studied your communication course, we did not really discuss this that much, because in all those communication course diagrams, this positive side of the signal and negative side of the signal they looked exactly the same. Why? Because the signal itself was a symmetric signal around its center frequency. So in your communication course, the signal always looked something like this. Very nice, symmetric. Positive side looks exactly like the negative side. And then when you modulate that, it becomes this one moving up and moving down. But both of them, they look the same. If they combine together, nothing changes. It's just an added amplitude, right? It's a nice thing, right? So if you bring them, if you have two versions of the signal, one at positive frequency, one at negative, again, the negative frequency is just a mathematical representation, but that mathematical representation comes in effect when you move the signal up in frequency. You can see that it has actually two bands appearing, right? Okay, so anyways, so when you bring the signal down, those two, they don't look the same. They are mirror of each other, right? And when you add them, you end up with something here that does not look like the original signal. So the signal itself becomes an image of itself, which means that it will self-interfere and self-corrupt when you bring it down to zero frequency, okay? Now, before going further, why in the communication course you always have this nice thing and we never discussed this issue? Why now we are discussing and showing you diagrams where the signal does not look symmetric around its center frequency? Why it's not symmetric around its center frequency? Is this true? Remember from your signals and systems course, right? When will you have this situation where you have a signal which is not symmetric around its center frequency, or in the base band, the signal does not look symmetric, so even if you bring it down to zero frequency, the signal looks like this, right? Okay, so it's not really symmetric. While in some other cases, specifically, for example, in the communication course, we show you something like this, very nice. For example, this, which is very symmetric, right? So why? Were we lying to you, or this is lying, or both exist, and what's the difference between those two? Remember from signals and systems, what's the difference?
I think the first one is the more natural form because we always have frequencies from 0 to whatever, and then we start moving it. But the second one happens when we start moving upper frequencies and non-linearities occur, so the signal changes.
Right. I'll come to you. I'll answer something that he said and come to you because you want to answer as well. So rethink your answer, because here I'm talking about two signals around 0. So we are not moving up or down in frequency. This is the baseband signal. Yes?
When the function is really not complex.
Yeah, that's the first case.
Yeah, it's symmetric.
Yes, and the second case, it's a complex in time domain.
Yeah, exactly.
So if the signal in time domain is complex, you will end up with something like this. If the signal in time domain is real, yani x of t is real valued only, you will end up with the symmetric situation. That's the correct answer. You wanted to say something else?
Related to, we're transmitting bits or transmitting analog signals. It
No.
depends on.
Not bits, not analog and digital. It has not. I mean, there is a relation, but the relation doesn't come from the fact that this is digital and this is analog. Tamam? Now the question is, does it mean anything to have a complex signal in time domain? No, it does.
The phase difference, right?
That's the trick, yeah. So the trick is when you have a combined signal carried over a sine and a cosine carrier, and you add them together, this gives you a complex signal in time domain, which means you will end up with a frequency domain that does not. So in reality, we do what in our transceivers? Typically, we have the signal coming, and then we split the signal into two paths, and then we multiply one with a cosine carrier, we multiply the other with a sine carrier, so it becomes two signals, one carried over an in-phase component, and the other one carried over a quadrature component, and then we add them together and we send them over the air, right? Now what's being transmitted over the air is two signals superimposed to each other, and they have a phase shift of 90 degrees. That's exactly what a complex number is. Tamam? And they are always orthogonal. At the receiver, when you multiply by cosine, you only get the cosine component, and you multiply by sine, you only get the sine component. So they keep always being orthogonal to each other, and you can always separate them again. Okay? So this is what we mean by when we use complex number to represent time domain signals. Because time domain signals, in reality, They are actually real values. The imaginary value does not have any meaning, and it is true, but they are two real values orthogonal to each other, right? That's what a complex number is all about, okay? So yes, we can have this situation if the time domain signal is complex. Is it true that we can physically have a time domain signal which is complex? Yes, when we have both sine and cosine carrier being used in our transmitters. And we'll see later on that because of the self-image, we will always have this. So it's kind of looping to itself. I will describe this in a few slides from now. Anyways, another situation where, again, without looking at time domain representation, another situation where you will have something like this, you can imagine that we are saying here that the different frequency components of the signal have kind of different shapes to them, is when you use FM modulation. When you are using FM modulation, what happens? At every single piece of frequency, you put a different, right, amount of energy, right? You put a different, so basically you spread your signal across the frequency in an asymmetric way. Now, if you want to represent that mathematically, it will end up being a complex signal in time domain. Right? But the whole idea is, even without noticing that we are adding a cosine and sine carrier, which is the more common case, FM modulation ends up producing some signals that when you take their Fourier transform, when you try to represent them in the frequency domain, they will look as asymmetric signals. They will not look as symmetric signals. Okay? So they are complex by nature. Okay? So anyways, so the situation of self-image can happen in many cases, and that's a problem with the 0-second IF. And how do we resolve this problem is going to be presented in the next few slides. This is just a quick exercise. I'm not going to stop at it. It doesn't have really much of calculations or anything, but just shows you that with 0 IF, we can only have self-image problem, but any nearby interferers will not really be imaged into your band of interest. The band of interest is what you are receiving here, okay? So that's just something simple. I'll leave it to you. It's very descriptive. It doesn't really have that much information to it. And this is a slide that describes the situation that I just mentioned. The fact that not always we have this nice symmetric spectrum. In many cases, we have actually the asymmetric situation, okay? And this is talking, when we talk about VCOs being used in modulation, this is directly FM modulation. So this talks about the FM signal, as I mentioned earlier. And in addition, this comes back to your answer. In addition to that, in almost all digital communication techniques, except the BPSK, the binary phase shift keying, but in all other types of digital modulation techniques, we end up with asymmetric or a complex signal. Because if you use phase, then the signal is moving between real and imaginary. So many components of the signal will have imaginary part. And if you use the FSK, it's again kind of frequency modulation, and we saw that frequency modulation by nature is complex. And if you use the QAM modulation, again by nature, you are using imaginary and real. So you always have this situation in almost all digital communication. This is why probably you mentioned digital versus analog, okay? Okay. How do we solve this problem? We solve this problem
By creating another problem.
but not really by creating more complexity only. So basically, we solve this problem by, rather than using, to demodulate the signal to the 0 IF, rather than using only a cosine carrier, so a single carrier, we use quadrature carrier. So we use cosine and sine carrier. So the carrier and itself shifted by 90 degrees. And then based on that, we should be able to achieve, if we look at the in phase and the quadrature component and add them together, after doing demodulation to 0 IF, the second stage, you will be able to see that the resulting signal here, after you add those two together, is going to be as if you have flipped the other one and added it. So it's no longer going to be that one of them, or basically what it does, in fact, is this. So when you do this operation, it's going to be effective. If you try to do it mathematically, it's going to be effectively as if you are getting this component. This comes from this branch, and the other component comes from the other branch. Basically, yes, that's what you do. You add the two together. So I said after this branch, you end up adding the two signals together to get your result. Okay? So you end up with, when you do the second stage, 0IF, using cosine and sine carrier, you will end up with no self-image problem.
But now we have more mixers, so more for.
Yes, much more problems, more complexity, maybe also mixers because they are noisy components. Yes, but
If you have an linear at the beginning, your noise figure will be.
yes, it's a more complex design, definitely. تمام? However, we will notice later on that most of nowadays designs, they always have this. So we don't really do the modulation with single cosine only, no longer. Not in any transceiver now. It's always two branches, I and Q. Yes.
What's the relation between L1 and L2? L01 and L02?
Relation relies, we will come to that, but the relation between LO1 and LO2. LO2, تمام؟ اللي هو LO1 is the one that brings you to the intermediate frequency. LO2 has to be the intermediate frequency, definitely.
It has to be the intermediate.
Yes, because you want to come to zero.
So
So the signal now is, let's say the signal came from 50 megahertz to 1 megahertz.
Okay.
You want to bring it down to zero, you have to multiply it by a carrier, which is 1 megahertz. So it's always the intermediate frequency value. That's LO2. تمام? Now this talks about what you were talking about, based on that relation between LO1 and LO2, تمام? And based on the fact that mixers are noisy components, we want to minimize the number of mixers in our, local oscillators create issues in our design. This is for local oscillators. Based on the fact that local oscillators create issues in our design, and I will talk about local oscillators in the next few slides, we'll see what kind of issues they create, okay? We want always in our design to minimize the number of local oscillators. We don't have to have one oscillator that works at 50 megahertz, and another one that works at 30 megahertz, another one that works at 20, separate from each other, right? Many issues, first of all, they can easily become out of sync from each other in terms of phase. So they can become, you can encounter some phase shifts between one oscillator and the other, which is a very common problem. In addition to that, oscillators are typically high frequency component with something called phase noise and frequency jitter. So they have some frequency variations. They cannot really be stable to the, like it's not really a single frequency. It's a frequency that drifts a little bit with allowable percentage, okay? Now, if this is the case, you want at the different stages, if a drift happens in one stage, the drift becomes the same in all other stages. If they are separate oscillators, this is almost impossible. In addition to that, oscillators also tend to create a problem that we'll discuss in the next few slides, that they leak back into the input of the system. And we'll see why this happens and how to overcome that problem, but it will come later. So anyways, in general, we want to minimize the number of oscillators in our RF design. And if we look at the heterodyne receiver with 0IF second stage, right? If we want to use a single oscillator for that one, then we end up with mandated values for our local oscillator values, right? So I want to create, for example, local oscillator that brings the signal to some intermediate frequency and then derive another frequency from the same oscillator to bring the signal finally to the baseband, right? Now, if I want to do this, the driving is called a frequency divider, and frequency dividers can only work in multiples of 2. So you can divide by 2, you can divide by 4, you can divide by 8, you can divide and so on. So powers of 2, sorry, not just multiples of 2. And similarly, we have something called frequency multipliers. They also work always in powers of 2. So you can multiply the frequency to double value, or to 4 times, or to 8 times, and so on. Because those dividers and multipliers are actually kind of counters. So So they end up being some powers of 2. They end up always being some powers of 2. We'll come to that, but roughly enough, we're not going to discuss the details of frequency multipliers and dividers in this course, but we'll come to describe a little bit about how they work a little bit later on.
Does that mean that for like a given input frequency, we have one LO or something like that, that when divided by 2, it will give us like...
Yeah, which means that you have to select this local oscillator. If you want, for example, if you decided, for example, that the ratio between your first local oscillator and second local oscillator is going to be divided by 2. And you are sure that the second one has to bring you to 0, and you know what's your input signal frequency, immediately it becomes mandatory that this local oscillator will have, if LO1 will have a certain value, right? Fixed, there's only one possible value for that, to bring you down to 0 in 2 stages, given that if LO1 and if LO2 have the relation that they are related to each other by one being half the other.
Does that mean that we cannot have like a variation in the input frequency?
Sorry?
We cannot have a variation in the input frequency?
Yes, we can have a variation in the input frequency, but that variation in the input, no, we cannot have a variation in the input frequency. That variation in the input frequency is going to bring...
If we have an input frequency that's different from the one we calculated for LO.
You have the band pass
لا لا
filters.
انت you will have a variation of the IF stage,
Okay.
not the input frequency. Input frequency can be anything. You multiply it by a local oscillator value, it will bring you to IF. The second one, that IF has to be brought down to 0.
Okay.
تمام؟
that is mean if the local oscillator 1, LO1, it can only be one value, right?
It
You
can.
have the band pass filter, so you already set your the input frequency to a specific band.
Oh, okay. But you will have the whole band.
I think it means like if you don't know the frequency that you're going to get.
Yeah.
Oh, or to completely? You
Or
mean?
like it can vary.
Doctor, I think he thinks LO1 is fixed at all times, the frequency of what you want. I think you can vary LO1 depending on the input frequency, right?
No.
You can.
Not very low.
مش very okay. You can do the calculation for a particular input frequency. Yes, you can do the calculation for a particular input frequency.
And then you're stuck with that frequency for...
But that's regular because because that's the frequency of your operating technology, right? The whole technology works in this. This is a band selection.
Getting the whole band.
Yes,
There.
yes. Well, that's what we do, right? We have a band selection. We bring the whole band around.
0, and then we manipulate it.
No. We bring the whole band around intermediate frequency, and then we do band selection, and then we bring all of that to 0.
Okay.
Okay? You got? It's clear?
Yeah.
Anyways.
Sure.
Okay. Yeah. Okay, so again, the characteristics of this, we call this the sliding. This slide just shows you that the intermediate frequency, the dividers shows you how a divide by 2 can do the operation. So basically, this is local oscillator 1. Now, local oscillator, if you think of it as a square wave, right? Then local oscillator 2 is just going to be as if it's a second bit counter, right? So the first bit counter is 1 0 1 0 1 0. The second bit counter is going to be 1 and it stays for 2 of this, and then 0 stays for 2 of this, and then 1 stays for, and so on. And if you take the third bit counter from the counter, it becomes changing every 8 of these, right? So 1 changes every 2, every 4 of those, and so on. Amen? So this is how you implement those frequency dividers by simply count. Why we use square functions? Because again, in oscillators, you can use a square function and then filter it out to end up with a sine wave and a cosine wave, right? You start with a square function, and then you put it through filters, you end up with sine or cosine. That's how oscillators also work.
Why did they shift by 90 degrees in the last one?
Because they want to generate, this is the same, so it's the same oscillation frequency, but this is for the I&Q that we use to overcome the self-image effect. Okay? And it talks here that it talks here about the fact that in the design of those frequency dividers, they can actually do dual functionality, so they can do the division of the frequency and also producing the quadrature and the M phase piece. So It produces two versions of the signal, the oscillation signal. One is a cosine and the other is a sine carrier in a single component.
One can work on the rising edge and one works on the falling edge or something.
Something like that. Yeah, it might be. I'm not sure. صراحة. It just says that it can do the dual functionality. It might be one way to look at it, yes. One works with the rising edge, one works with the falling edge, maybe. Now,
Can we use the same local oscillator with no multipliers or divisions
and then do what with it?
to bring it back to zero?
How do you do that?
Because if we, for example, subtract, if we multiply by a certain frequency, and we can consider that subtracting that frequency, maybe if you can divide it into two parts, so takes it 50% of the way to zero, and then the other 50% is done, so that eliminates the...
That's one way, yeah, that's one, but that's a special case, yeah. Special case of the general solution. The special case that you are talking about is that we will always bring the signal to halfway.
Yes.
So the IF for us is always halfway where the carrier is. In that case, yes, but that's a very special case. Yeah. Okay. So in that case, the second is also going to be the same frequency, bringing the signal down. Yeah. Okay. So here are the calculations. So if you have F local oscillator 1 plus half F local oscillator 1, that's the first one. That's the one that brings the signal to some intermediate frequency. And then the second one, half of F local oscillator, that's the one that should bring it to zero. The sum of those two should be equal to the original carrier of the signal, right?
Yes.
And then accordingly, you end up with that the local oscillator 1 is going to be 2/3 of the input signal to bring the signal down to zero frequency. Tamam? Okay. And the FIF, so the intermediate stage that you will work on, is going to be always 1/3 of the original signal carrier. Tamam? The other one is something called the fractional or the normalized bandwidth calculation, and this shows you that that normalized bandwidth does not change when you are using the IF stage. It stays the same. So yes.
It does not always have to be the third, right?
Does not always have to be the third. Why?
Can you not choose another intermediate frequency other than the third of the input?
And you still satisfy bringing the signal down to zero?
Depends on the divider. I think it will depend on the divider.
احنا هنا بنتكلم على the case where the divider is 1/2.
Okay.
So we are using the yes, it depends on the divider. صح. هنا بنتكلم على case انت بتتكلم in general. So if we don't consider a divider of 1/2, if we consider the second stage something else. Okay. Yeah, but for solving for 1/2, it has to be this. For his case, for example, when he said the same, so it's the same carrier, the same local oscillator, so it has to be you bring it to half. Yeah. Okay. طيب. Now we move to the receiver architecture, which is total. All the previous ones that we talked about were enhancements to the heterodyne receiver. Okay. Now we move to another, which is kind of more modern. So currently, most of the digital communication equipment, they use this architecture, which is called the direct conversion architecture. So you don't really use any intermediate frequency. This is the one that you studied in your communication course. You take the signal to the carrier, you take the signal down to zero, right? Why this was not used in the past? Because doing this, again, with the capabilities that we had in the past, in early days of radio communication, was very challenging in terms of filtering requirements, right? So in this case, you have to make sure that you can filter not just your band, but you can actually filter even your channel early on in a very accurate way. You don't really use any intermediate frequencies. And also, because in many cases also the direct conversion requires oscillators with very high frequency, which is quite difficult to implement both in the transmitter and the receiver in older technology and maintain it with small size within a chip. With newer technologies and with better silicon capabilities, now we can have oscillators and mixers very high frequency operational capabilities, and they can still be integrated inside the chip. So with the advancement of the RF chip technology, the direct conversion became a possibility or something good. The nice thing about the direct conversion is that you remove the idea of image from your mind completely. So you don't have an image issue here because you don't come to any intermediate frequency. And also the nice thing is it looks simpler, right? So your receiver comes only in a single stage. You receive the signal, you band pass it to do the band selection, low noise amplifier to bring the signal to a reasonable level, multiplied by the same carrier that it was carried on, you bring it down to 0, and then you do your selection of the channel at the low frequency, at the very low frequency, right? Because you do it now as a low pass filter rather than a band pass filter, which is a much simpler design, okay? The challenges were in the frequencies, the higher frequencies that you need to accommodate both in your oscillators and your mixers. Tamam? Okay. Now it became possible. So why do we have a sine and a cosine here? Exactly, because even if you bring the signal directly at once to 0, if it's not symmetric, you will end up with self-image. So that's why for direct conversion, you have always to use the quadrature, the two components, sine and cosine. Okay. Problems, nothing free of problems, tamam? Because of the higher frequency here, and not only that, because the fact that your local oscillator produces a carrier which is exactly matched to your incoming signal, now you can do two things. You can affect other transceivers around you, and you can self-affect your own received signal. Tamam? Where does the bad effect come from? It comes from something called leakage problem.
Not parasitic capacitance.
Yes. So it's because of the parasitic capacitance, the local oscillated signal generated from the local oscillator here can leak back into the input of your system. Not only that, it can actually even transmit around you, tamam, in an undesired fashion. طيب, the problem of leaking back to yourself, tamam, is one thing, and the problem of affecting other transceivers is another thing. What's bad? Okay, affecting other transceivers is probably clear. What's bad about leaking back into myself?
You damaged your signal amplitude.
The next signal.
بس الليكنج اللي طالع من هنا طالع شكله ايه؟ It's just a carrier in the middle of my signal. ايه المشكلة؟
I mean, there is the frequency deviations that happen from the local oscillator.
افترض انه مفيش deviation.
It will add up with the signal.
So when it adds up with the signal, what does it produce?
The LNA saturate.
Why?
Because like you're adding more.
Yeah, so basically this signal, this local carrier coming from here, will end up being what at the output here?
Amplified.
DC offset.
DC offset, exactly. That's the second problem that we'll discuss. So the first problem is the leakage that comes from here creates a signal that can affect other receivers. That's one problem. The other problem is the self-effect here is going to be mostly introduced as a DC offset. Because you have a cosine with fixed amplitude, which is being demodulated by itself. Right?
Okay.
So you end up at the output here. This leakage ends up being a DC offset at the output of the, yes?
I have a question. Does this relate to the DC offset? Okay, so I was working with the hack RF, and then when I was looking at higher frequencies, like the demodulated frequency domain of those, for example, the FM modulated signals. So I'm looking at the FM band. I was always noticing that there was in the middle, at the zero hertz, there was always a DC offset. Was this related to the local frequency running at higher frequency?
I have no idea. It might be also your signal. It might be your signal itself has a DC. I don't know.
I tried shifting it, but the DC offset always was there, and it was.
Then it might be. I cannot, because DC offset comes from many things. This is just one effect due to local oscillator in this architecture, right? It might be coming from this. It might be coming from something else. I don't know. I cannot answer. I mean, that it's a possibility, but it's not the only possibility. Okay. So why DC offsets are bad? Because again, the effects that you mentioned, it can easily saturate your amplifiers and cause issues with your received signal. I'm not gonna go through this. It's here only for demonstration. This is kind of showing you one type of amplifier, cascade low noise amplifier, and then doing the modeling of this, the small signal modeling of this amplifier, and then doing the analysis, and you can figure out from this analysis that there is some leakage which is going from the output into the input. That's the whole idea of this analysis, but it's out of the scope of what I want to do in this course. So I will leave it to you. I was actually deciding, should I remove the slide or keep it, but I thought of keeping it for your own reference. It's in the book as well, but you can look at it if you want in your free time, and if you have questions, you can come and ask me. So I'm not preventing you from asking me, but it's not part of what I want you to do. DC offset problem. This example shows basically how the DC offset problem happens and in terms of calculation. So I want you to try to calculate this. It says that you have a direct conversion receiver which is incorporating a voltage gain of 30 dB. So this from here to here, the voltage gain is 30 dB in this stage. From the LNA input to the each mixer output. So to the output of the mixer, the cosine and the sine. Okay? And another gain of 40 dB in the baseband stages following that. So from this point until the signal reaches here, the amplitude of the signal, which is called the voltage gain, is going to have another gain of 40 dB. So what you see here is going to be 30 plus 40, which is 70 dB amplified as compared to the input to this low noise amplifier. Okay? The question says that if the local oscillator leakage at the low noise amplifier input, so this guy is leaking, local oscillator, and it's leaking to the input of the low noise amplifier. Okay? And the amount of leakage is equal to minus 60 dBm. Okay? So this leakage is minus 60 dBm. Okay? Determine the offset voltage at the output of the mixer. So the DC offset here, right? So it wants you to determine when this guy goes through again, what's gonna be the DC or DC offset here?
10 dBm.
10 dBm.
Yes. Yeah.
Which is a lot.
10 dBm.
Which is a lot.
Which is not a small amount. Yeah, exactly. Right? طيب. ليه 10 dBm؟ ده السؤال.
Minus 60 plus 70.
صح. Yeah. فين ال 70؟
30 plus 40.
Okay.
But wait,
No.
we're catching the
No.
DC offset where?
No.
It's not.
احنا عايزينه هنا على فكرة.
We're catching the D, yeah, so
No,
should
I
be
want it here, not here.
negative 30. Should be negative 30. Should it not be negative 30?
Because you have 30 at 30, 30 down and 30 up.
احنا مش عايزين انا عايز voltage عايز
Actual
voltage.
But do you consider leakage only from one oscillator or like?
لا on one branch. ما هو دول two parallel branches فاحنا بنتكلم على one branch only. You don't need to look at both branches. يا اخوان determine the leakage voltage offset voltage. عايز ال DC voltage مش ال dBm مش amount of power. Amount of power you directly calculated as you did, but we want the voltage. ها
The voltage.
يلا.
لو كان 20
10 power.
over 20,
Yes.
10 to the power of 10.
For, is it because before rectification it will not be DC yet, it will be a rectified cosine, like squared cosine.
It's cosine. It's not a DC. الريكتيفيكيشن هيحصل لما تضرب هنا، لما تضرب الكوساين في الكوساين بيطلع لك
Squared cosine.
بيطلع لك سكوير كوساين which is a cosine at double frequency و DC. both of them هو عايز الدي سي بس.
31.6 millivolts.
ده
31.6 ملي فولت. لا انت كده حسبت 31 دي اللي هي 30 دي بي دي calculated in voltage gain in absolute gain. ده بس لسه وبعدين انت you need to use this to figure out how this will map into a value. انت في عندك minus 60 dBm at this point. تمام. Simply you need to figure out what's the voltage amplitude of this signal اللي هي leaked back. This is represented here by dBm. You need to represent it as amplitude of cosine. تمام. وبعدين using the amplification factors that you have here, you can figure out what's gonna be the DC offset at the output of تمام. So what you did, Mustafa, is you only calculated that this 30 dB is equal to approximately 31.6 in absolute gain, absolute voltage gain.
But what's the input?
تمام. الانبوت ما هو كاتبه لك بالدي بي ام.
Yes.
You need to convert that to voltage.
Convert also the
Assuming what? When you convert to voltage, we always assume what?
1 million volt.
50 ohm.
50 ohm load.
50 ohm.
So you always assume that you are across a resistor of 50 ohm. So basically this is a power value, which is V square over R, but you need to convert it to watts or milliwatts. And then using V square over R, you can figure out the voltage here. Once you figure out the voltage here, you can easily figure out what's going to be the DC output at that point. تمام؟ حد يعرف يحسبها ولا؟ هو ironically تمام؟ That's why I stumbled a little bit at the number that he said. Ironically, it's gonna be the output here is gonna be 10 millivolt.
Yeah.
So when he said 10 milliwatt or 10 dBm, it was like 10, how did he figure it out that quickly? But then he was actually calculating dBm at the output here. So I was, okay, how did it happen? Okay, so if you do the calculation, هو محلولة في الكتاب عشان ما نضيعش وقت كتير فيها. If you do the calculation, هو عمر فاتح الكتاب. ما انا تخيلت انه كمبيوتر كده. If you do the calculation, you will have 10 millivolt here, which is going to be approximately 1 volt at the output here. And 1 volt, by the way, at the output of this is typically the next stages are digital stages اللي هي في البيز باند كلها. 1 volt at your digital stages is really high. It's not a small thing. تمام؟ The amount of DC that comes from that leakage is not something that you can neglect. You have to do that. So how do we, first, this example shows you, again, this requires you to do some calculations in terms of the DC voltage and then calculating how it maps back into the input, but both at the sine branch and at the cosine branch. And you will end up finding out that the two components, the DC that leaks into the I branch and the Q branch, they are not exactly the same.
Are not.
Not exactly the same. They have two different values. And the reason for that is, again, the cosine and the sine goes back to the input.
Yes.
Tamam? And then they feed, the cosine and the sine feeds on the cosine branch, and the cosine and the sine feeds in the sine branch. Tamam?
And then they're added up again.
And then if there are some phase shifts between them, tamam? The phase of the, if they go through different circuits, which is most of the time, for example, the branch that goes for the I and the branch that goes for the Q has some imperfections in their manufacturing, so there is a slight change in terms of the wire lengths or whatever. This is going to induce some phase called the phase of the circuit between the sine and the cosine component. And because of that, you end up with the values here are not simply just the V leakage multiplied by the local oscillator, but one of them is multiplied by cosine some phase shift, and the other one is multiplied by the sine of that waste phase shift. And we know that the cosine and sine generally are not equal. Even though it's the same phase, but the cosine and sine are not equal except in specific values اللي هي فين؟ pi over 4. تمام؟ So you end up with two different values for the DC that gets induced in the, again, this is from a practical perspective, not in the ideal case. تمام؟ So generally speaking, you might end up with two different DC offsets.
In the ideal case, they should be.
Yes, if you don't assume that there are phase differences, there are no small changes in terms of
Because of the small change, the
oscillator.
value of the
Yes.
cosine is different from the value of the sine. And
Yes, they end up being different. Yeah. How do you solve the problem of leakage, well, the simplest solution or a passive solution is going to be using a filter that actually notches the signal at the DC. So you try to remove the DC component of the signal, تمام? Hoping that your actual signal does not have that much power in the DC. So if your actual signal is something like this, then removing this part is going to affect your signal itself. تمام? While if your actual signal is something like this, removing this part is not going to affect your signal and it's going to remove that carrier that leaks back into the input. Okay? This filter, which is very narrow at a certain frequency and it accepts all other frequencies, is called the notch filter. It's a special type from the general category that's called band reject filter. So it's rejecting a certain band and accepting all other bands. Okay? But in the case it's very narrow, it's called a notch filter. And here it talks about if you try to calculate the corner frequencies based on some rules of thumb. Okay, so the rule of thumb says that the corner frequency of the high pass filter F1 is equal to 2 pi R1 C1 minus 1. This corner frequency, the rule of thumb says that it must be less than 1,000 of the symbol rate. So if this notch filter has a corner frequency which is of comparable value to your symbol rate, to the rate of your transmission, if we are talking about digital transmission here, then you will end up with the different symbols interfering with each other. We call that inter-symbol interference because the symbol can no longer maintain its shape as a square. It spreads a little bit because of that filtering effect, and then it has a significant value affecting the next one. Like you have a symbol, you know what's inter-symbol interference, right? You have a symbol, here is a 1, and then the next one, let's say, is 0. Okay? Now, if this for some reason becomes wider, and that notch filter can cause that effect, if it's very close to the rate of transmission, right? Then this means that this will have some value where you are trying to read the 0. And you will end up with something that might read as a 1 even. Okay, because of that spreading of the symbol. And each symbol will cause the same effect to the next one and so on. This is called inter-symbol interference. In order to make sure that this effect is negligible, you have to have that notch filter corner frequency, which is the frequency when it starts to drop. That's called the corner frequency. Amen? That corner frequency has to be at least the symbol rate divided by 1,000. If it's smaller than that, if it's larger than that value, then it becomes a problem in terms of inter-symbol. That's kind of a practical rule of thumb. That's why we call it a rule of thumb. It just comes from practical designs. Okay? So that's one solution, which is the passive solution using notch filtering. Another solution, which is an active solution, using feedback and different stages of amplification. So your signal is coming from here, right? And then you take it through. This is supposed to be your amplification path, the normal amplification path. Okay? And the total gain of this path is the multiplication of GM1 multiplied by the RD multiplied by the amplification A. Okay? This GM1 multiplied by the RD comes from the voltage created here, and then the next stage is multiplied by the amplification factor here. This gives you the output signal. Now you take that output signal, you filter it so that you pass more or less something close to the DC component, and then you amplify that with a negative gain such that you almost subtract the DC component from here. Right? So that this is kind of like a plus sign, as if those two are going to add up. Okay? So the whole idea here is to, as if you are, it's just a schematic by the way, it's not really an actual circuit design. Right? So the whole idea is by taking the output, low pass filtering the output so that you can get something very close to the DC component, and then as if here you have measured the DC from this output, you multiply it by a specific negative gain that makes sure that it becomes at the output here equal to the actual DC value before going through this stage, because you are sampling after the last stage, right? And then when you add this negative to this input, you will end up with DC removed, but in an active fashion. The previous one was in a passive fashion. Again, I'm not that much concerned, even though they are simple amplification and feedback circuit calculations here, but I'm not really much concerned about these calculations as opposed to understanding the concept itself. Tamam? So we have the passive, just taking it through a filter, a DC block filter in the previous case, or the active, which is using feedback circuit. Okay, it continues with the calculations of that feedback circuit, and I will stop here. This is what